Okay, Mr. Nagy's Physics 11 class here, and we're dealing with the momentum energy unit still, and we've been talking about last day getting into energy and conservation of energy. So here let's talk a little more, and we've had some problems already on this, but let's talk more about energy transformation. Key thing here, and I've picked up a picture of a Hot Wheels track. Let's make it just a little bit bigger, just so we can see a little bit more here. So let's say we've got a little Hot Wheels car. I think red will show up pretty well here. And it starts up here, and it's some distance above the desk. Okay. And so because it's got some height, and we're just saying for reference that this desk down here is a height of 0. So we're some height here. So at this point, let's call it point 1, we've got potential energy, right? And that is equal to the total energy that this thing has. Now, as we release that car, it's going to roll down there, and that energy is going to be transformed into kinetic energy. At the bottom, it's no longer got any height. It's right down there at point 0, but it's still got energy. And in the perfect world, it's got kinetic energy. EK equals ET, the total energy, at point 2. Now, it's going to get back up here and cruise along, and it's getting up high here where it's not as high as it was originally. So let's call this point 3. At point 3, the total energy is equal to the kinetic energy plus the potential energy. Okay, I'll put my bracket, I guess, on the other side there. But it's got kinetic and it's got potential, and we could figure out both of those if we knew the height. We could figure out how high something's going to roll up a hill on the other side. So we've done a fair bit of that now. Just the idea that energy is conserved. The total energy, whether we looked at that PhET lab or whatever, is always constant. Of course, in the real world, it's not always conserved. In fact, we have friction along the way. So we lose energy right here. Lose energy. We lose energy all the way along, right? And that's going to tie into efficiency. Now, we found our track was about 60% efficient in our Hot Wheels activity there. And what that means is 40% of the energy that it has is lost to friction. Okay, so let's do a little example right here where we combine a couple of different concepts. I'm just going to take this picture again, and I'm going to give us a little bit of a different scenario. I'm going to paste the picture there. I'll make it big again. We're starting from scratch. So let's take a car, and we'll make our car red again. And we're going to start it up here from, it's going to be about 1.2 meters high to begin with. Now, just like our track before, our track is going to be 60% efficient. That is, it's going to convert the potential energy here at a rate of 60% into potential energy here, EP, into kinetic energy here, but it's going to lose 40% of its energy. Now, we're going to have this car here, the red one. It's going to be, let's make it 0.2 kilograms. Kind of a big car, but it's easy to mess with. Now we're going to throw a little curveball into things here. We're going to have it hit another identical car at the bottom, and that one, boy, that's tough to see, but it's also 0.2 kilograms. Okay, and then they're going to join together when we get to the bottom. And we're going to ask, how far up this track is it going to go? Now, I'm going to throw one little bit of a caveat in here. I'm going to say the track changes, and here it's 100% efficient. Okay, realistically it's not any different, but we're going to ask the question, how high will this combined wreck go after the collision? So we've got a bit of a conservation of energy problem here, but we've also got some momentum going on because we've got a collision going under or taking place, so we need to take that into account. So let's see, for convenience I'll number these areas here. Number 1, at point 1, the total energy is equal to the potential energy, and that's going to be mgh, and so that's this thing was 0.2 kilograms, g is 9.8, and the height is 1.2 meters. So the potential energy, I'll use my calculator, not on the screen here, 0.8 times 1.2 equals, I got about 2.4 joules of energy. Okay, at the bottom I would have 2.4 joules of energy, except I'm going to lose 40% of it. So I'm going to put right down here at point 2. At point 2, the E total is only 60%, that's 0.6, of E total at point 1. Okay, so here at point 2, the total energy is 60% of what I had at point 1, so it's 2.4 times 0.6 equals about 1.41 joules. Now all the energy I have here, E total is kinetic, that's in joules there, right? I'm no longer any height above the bottom there. So the total energy I have here at point 2 is 1/2 mv squared. So 1.41 is equal to 1/2 mv squared. So this thing's going 2 times 1.41 divided by, what was the mass? 0.2. And I'm going to square root all of that. So my speed at the bottom is square root about 3.76 meters per second. Now, running a little low on room. To save myself some room, I'm going to go over here. Here's what's going to happen during the collision, and the collision is going to be at point 3. Whoops, point 3, the collision. Okay, well, energy is not conserved in the collision. There's going to be a crumpled wreck, there's going to be friction, there's going to be noise. Okay, energy will not be conserved, but P before is equal to P after. And again, kind of slack here, I might want to put a summation sign, doesn't matter. What have I got before? I've got a red car, and it's it's 0.2 kilograms, and it's moving at 3.76, and I've got a purple car, and it's stationary. And then after, I've got a red car and a purple car. Whoops. And so that's going to be a total of 0.4 kilograms, and I want to know how fast they move off at. This was also 0.2. So what we've said is mv plus mv equals mv. That one's 0 because the velocity of that one is 0. Okay, so the velocity of the crumpled wreck that I'm looking for here, and I'll put that as C for crumpled wreck. How's that do? And C, and this is the red car, and that's the red car. So the velocity of the crumpled wreck is mass of the red car, velocity of the red car divided by mass of the crumpled wreck. So it's, excuse me, 0.2 times 3.76, right, is what I was, yep, divided by 0.4 as they're combined. Sorry, to save on room here, I'm going to write over to the side. So it's just going to be 1.9 meters per second, roughly. Okay, so it's 100% efficient now going up the yellow side of the track. I wish I had more room, but so I want to figure out how high. So I've got kinetic energy here. Let's see, what color can I go to? I'll go to this color here at 0.4. So at 0.4, I've got 0.4 kilograms of stuff moving at 1.9. So at 0.4, I've got kinetic energy only. I'm down at the bottom of the track, so it's 1/2 mv squared. That's my total energy. Okay, so it's 0.5 times 0.4 times 1.9 squared equals squared times 0.7. Sorry, not meters per second, but joules of energy. And as I go up the track, I'm going to keep that energy because I'm 100% efficient, but at the top my total energy is going to be 0.7 joules. So let's call this at 0.5. At 0.5, E total is equal to E potential. So 0.7 is equal to mgh. So h is equal to 0.7 over 0.4 times 9.8. So this thing's only going up. 0.18 meters. Okay, so the trick to this problem, to these problems, is the idea here that energy is conserved on the track. Well, here we've got some energy lost. Of course, that loss is to friction or heat, the same type thing. So the wheels have heated up or something. Energy is lost in that collision. And on the other side, we imagine that energy was totally conserved. So we've got a couple of things going on there that we're dealing with. We're talking about energy transformations. We're talking about momentum conservation. We're talking about efficiency. And the last thing we said we're going to talk about here on this particular video is power. So I'm just going to give you a quick overview and we'll look at it in class next day. Power is the rate at which energy is transformed. Energy is transformed. Okay, so power is equal to, well, there's a change in energy. That's an energy transformation. And per unit time, if you like, rate is always something per second, per minute, per hour, right? Your rate of pay. And of course, we've already said before that a change in energy happens whenever work is done. So power can also be expressed as work done per unit time. In any case, the units are, well, energy is in joules and time is in seconds, our basic unit. And same thing here, joules and seconds. And we have a unit for, again, named after a famous dead guy. The unit for power is the watt. Okay, so 1 watt is equal to 1 joule per second. You may have heard watt used for things like, well, like a 60 watt light bulb. Your sound systems, so many watts output of sound energy, right? Pretty famous. A watt is really not a whole lot of energy. In fact, if you had Nag standing here at the front of the class, there's Mr. Nag, and I was lifting a, well, let's say it's a 100 gram mass, so that's 0.1 kilograms. And the force of gravity on that is going to be about 0.1 times 9.8, so that's about 1 Newton, approximately. Okay, there I am, happy guy, standing at the front of the room. And I lift that thing 1 meter, and so that's not that high, imagine that. I lift 100 grams, and that's about the size of your calculator. Okay, so I lift my calculator 1 meter. Then I've done work is equal to force times distance, and that's 1 Newton times 1 meter. I've done 1 joule of work. If I lift this in just 1 second, then the power output of Nag is work done per unit time, so it's 1 joule in 1 second. That's 1 watt. Just so you got a bit of a feel for what a watt is. Now we're going to look at machines that do kilowatts of work. We put a prefix on this. 1 kilowatt, of course, it's going to be 1,000 watts. Okay, a lot more energy, and in fact we'll even look at an old unit called the horsepower and talk about where that comes from. So that we'll delve into a little more in class.